So hello everyone, how are you all? How was your Diwali vacation? And I hope you're all good and safe. So am I audible and visible to all of you? Can you hear me? Just put it in the chat box if you can hear me and see my screen as well as me. Yes. Yes. Thank you so much, Anjana Sri. So hope you all have enjoyed your vacation. So do you remember what I have discussed in the last class? That is on last Friday. So we are in general organic chemistry lesson, and can any one of you remember and tell me the name of the topic that we have discussed at last on last Friday? I hope all of you were there on the on Friday, right? So what is the name of the topic? I'm just asking you the name of the topic only. Very good, Anusha. Yes, it is nomenclature. Good. So we were discussing about the nomenclature for unbranched system and for branched system hydrocarbons, and for the system which has one functional group and more than one functional group, right? So that topic was over, and now in today's class, as I've told you, we are going to discuss with the isomerism in organic compounds. Okay. So the learning objectives for today's class is the isomerism and its two types. The two types of isomerism are structural isomerism and stereoisomerism. Okay. So we are going to completely deal with this isomerism topic. And if we are able to complete this isomerism topic within the time, then I'll move on to the next topic. Okay. So now coming to the isomerism. What is isomerism? Iso means same, right? Iso means same. So the phenomenon of existence of two or more compounds possessing the same formula but different properties is called as isomerism. Okay. So the compounds having same molecular formula but different chemical properties and different physical properties are called as isomers, and the phenomenon is called as isomerism. Got it? So this is very important. The system will have same molecular formula, but they will have different properties. Got it? So now under isomerism, there are two types of isomerism. One is structural isomerism and the other one is stereoisomerism. So I'll come to the definition of structural and stereo to you later. Under structural isomerisms, still we have four classification under this. The first one is chain isomerism. The second is positional isomerism. The third is functional group isomerism. And the fourth isomerism is metamerism. Okay. So these four are the classification under structural. Now coming to the classification under stereo, the first is geometrical isomerism and the second is optical isomerism. So these two are the stereoisomerism. Got it? So you should know the flow chart of isomerism, and this is the classification of isomerism. Got it? Now we will discuss one by one. Okay. So first I'll start with the structural isomerism. So what is meant by structural isomerism? What is meant by structural isomerism? So the compounds having the same molecular formula but different structures are called as structural isomerism. So in all the cases, molecular formula will be same, but if the structures are different, then it is called as structural isomerism. So in all chain, positional, and functional and metamerism, if you see, the structures will be different. Okay, that's why they are coming under this category. So coming to the first structural isomerism, which is called as chain isomerism, the definition for chain isomer is, so the two or more compounds having similar molecular formula but different carbon skeleton. So what is a chain isomer? The system which has same molecular formula but different carbon skeleton is called as chain isomerism. So I'll show you some examples to understand this part. So I have took a C5H12 as the example for you. Can you tell me the name of C5H12? Can anyone tell me the name of C5H12? It is a hydrocarbon and it is a saturated hydrocarbon which contains 5 carbon. Saturated means it should be an alkane, right? 5 carbon containing alkane is called as, what is the name of this hydrocarbon, students? Very good. Yeah. Yes. It is pentane. Good. It is pentane, right? So the pentane has some chain isomer. Yes, good. Good, Saroja. It is pentane. So there are some isomers existing in this pentane. So the first is N-pentane and the second is isopentane and the third chain isomer is neopentane. Okay. So in case of pentane, you see, yeah, the IUPAC name of isopentane is 2-methylbutane, which you can see here, and IUPAC name of neopentane is 2,2-dimethylpropane. So I hope you should be able to give the IUPAC name for the given compounds, right? So have you all studied the nomenclature part in your vacation? I should have not asked this question, right? Okay. So here it is called as 2-methylbutane because 1, 2, 3, 4. This is the parent chain, and the second carbon methyl group is there. That's why it is called as 2-methylbutane. And here, if you see, this is the longest chain. Either this or this, anything you can take. And if I number, it is 1, 2, 3. And to the second carbon, 2 methyl groups are attached. So it is called as 2,2-dimethyl. And the parent chain has 3 carbons, so it is called as propane. 2,2-dimethylpropane. Okay. So these are the IUPAC names. Now these 3 compounds are the isomers of each other. Why? So in case of pentane, you can see the carbon skeletal structure like this. So this is pentane, right? So all the edges, they are carbon. So all the 5 carbons are in the linear fashion in case of pentane. In case of 2-methylbutane, so this is butane and here is the methyl group. And in case of dimethylpropane, to the second carbon, we have 2 methyl. So this is the structure. So what is happening here? So the molecular formula is same for all the 3 compounds, but the carbon skeleton differs. That's why it is called as chain isomer. Okay. So one is in a straight chain manner. The other compound is having 1 branch and the third compound is having 2 branches. Got it? So they differ in the branches, which is nothing but the carbon skeleton. That's why it is called as chain isomerism, and it is given as an example to you. Okay. And if the question, if they are asking you to find out the number of chain isomers possible for C5H12, means what you have to give. How many isomers are possible for C5H12 formula? It is 3. Okay. Number of possible chain isomers existing for C5H12 is 3. Got it? So this is one type of question you will get from this, and one more type will be like they will give you one isomer, one compound they will give you, and they will ask you to find out the chain isomer of this particular compound from the given options. Okay, so they will give 4 options and you have to find out the chain isomer, I mean the other compound of C5H12 or to the formula which they are giving. Okay, got it? Any doubt in the chain isomer? Shall I move on with the next isomerism, which is positional isomerism? Students, if it is clear to you, just put a thumbs up or yes, yes. Okay, thank you. Thank you so much. Now I'll go with the second isomerism, which is positional isomerism. So what is positional isomerism? So the 2 compounds or more than 2 compounds differ in the position of the substituent or the functional group on the carbon skeleton. Okay. So they will have same molecular formula, but the position of the functional group will differ for both the compounds. Got it? Position of the functional group. So in case of C3H8O, we have positional isomerism existing in it. And you can see the first compound is propan 1-ol, and there are 3 carbon, 8 hydrogen, and 1 oxygen, you can see. And the IUPAC name is propan 1-ol because OH attached to carbon is 1, 2, 3. So since it is having 3 carbon, it is propan, and OH is attached to the first carbon, so it is called as propan 1-ol. Okay, and isomer of this compound is propan 2-ol. And here you can see the OH is attached to the second carbon. So what is differing here? Functional group is same or the substituent is same, but the position of the functional group attached to the carbon is differing. Got it? So that's why it is called as positional or position isomerism. Okay. So one more example I'll show you for a C3H9 and N formula. So you can see propan amine. So this is 1, 2, 3. So what I can say? So more appropriately, I can write like this. Yeah. Positional isomerism is also a structural isomerism only. So in that flow chart I have showed you, no? Under structural only, chain, positional, functional, and metamer. Everything comes. Got it? This is the second structural isomerism. Second structural isomerism. So the formula remains same, but the structure differs. Got it? Yeah. So coming to the more appropriate name for this propanamine, it is propan 1-amine. We can write like this, no? It is propan 1-amine. And the isomer of this is propan 2-amine. Since NH2 amine group is attached with the second carbon, it is called as propan 2-amine. So you can see the position of the functional group changing. So who is the functional group here? Amine is the functional group. So the position of amine changes in both the compounds, and it is called as, or it is one of the example for position isomerism. Got it? Clear? Any doubt in positional isomerism for anyone? If there are no doubt, give me a thumbs up or type yes in the chat box. We will move on with the next isomerism. Shall I go on with the third isomerism, students? So what is the third isomerism? Do any of you remember? Yes, Bhavana, thank you so much. And do any of you remember the third isomerism, which I have showed you on that flow chart? Very good. It is functional isomerism. Good. So what is functional isomer? So two or more compounds having the same molecular formula but different functional groups are called as functional isomerism. So here, functional group itself is going to differ for both the compounds, for the isomers. Okay. So I'll show you an example for C3H6O. So you can see a compound on your screen, which is called as propanone. So what is the name of the functional group present here in propanone? So can you guess the name of the functional group? The class of compound that we have discussed on last class. What is the name of the general name of the functional group here? It is ketone, right? It is R. Yes, good, Anusha. It is ketone. So R, CO and R we are having. So it is ketone. And now for the second compound, it is CH3, CH2 and CHO. So now here, what is the name of the group present in this compound? It is aldehyde, right? CHO is called as aldehyde. CHO is called as aldehyde. So it is called as propanal. You can see it is called as propanal. So the formula is same for both, but you can see the functional groups are different. One is ketone and the other one is aldehyde. Okay. So can you able to differentiate between positional and functional? In positional isomerism, both the compounds will have same functional group, only the position will differ. Whereas in case of functional isomerism, functional group itself will differ for both the compounds. Okay. Isomers always exist in pairs. Isomerism always exists in pairs. You cannot take one compound and say that this particular isomerism is existing in this compound. Like that we cannot say. We have to take, we need at least two compounds to explain the isomerism. So in that two compound, If both the compounds are having different functional group, then it is functional isomerism. So like this ketone aldehyde pair, we do have some other pairs also. I'll show you those pairs here in the next slide. So the next pair is alcohol and ether. Okay, alcohol always pairs with ether. So you cannot take alcohol and try with ketone or aldehyde. Okay, the formula will not get satisfied if you treat alcohol and if you try to match it with some other group. Got it? Only if you try to match it with ether, you will get the formula and the functional isomeric pair you will get. So what is the functional group for alcohol? For alcohol, it is ROH, right? And for ether, what is the functional group for ether? It is ROR. So both R can be same or both can be different. I'll show you examples for all these in the next slides. Okay. First, I'll tell you the pairs. So first pair is alcohol and ether. And the second pair is aldehyde and ketone. And for this only, we have seen the example just now in the last screen. So the group for aldehyde is RCHO. And for ketone, it is RC-double-bond-OR. Okay. And the third pair is cyanide and isocyanide. What is the functional group for cyanide? For cyanide, it is RCN, right? And for isocyanide, it is RNC. RNC is the formula for isocyanide. And the fourth pair is acid and ester. What is the group for acid? Carboxylic acid. It is RCOOH. And for ester, it is RCOOR. Right? So this is the ester. And the fifth pair is alkene with cycloalkene. Alkene, what alkene we can take? Minimum we have to take the 3 carbon containing alkene, which is called as CH3, CH double bond CH2. So this is an alkene. This is an alkene and the isomer will be cycloalkane. So the 3 carbon containing cycloalkane is cyclopropane, right? So now these two are the isomers. You can see the both the compounds are having the same molecular formula, that is C3 and H will be 6. Got it? So this is the fifth pair. Now among these 5 pairs, the very important pairs are alcohol and ether, aldehyde and ketone, acid and ester. So these 3 all are very important, but very important pairs are these 3. Got it? So you should not take an acid and try to match it with ketone. You will not get. So in acid, we are having 2 oxygen, right? So in ketone, only 1 oxygen will be there. So you cannot make the isomeric pair of ketone with acid. So always try to remember the pairs which I have given you for functional isomerism and try to match it accordingly. Got it? Clear? Shall we move on to the examples for each pair? So any doubts so far for any of you? If you have any doubt in between the class, you can put it in the chat box. Okay, I'll make you clear with that. So now I'll go with the examples. So the first pair is alcohol and ether, and the general formula will be CnH2n plus 2O for alcohol as well as for ether. So these are the functional general groups for both. And the example for this system is C2H6O. So C2H6O for alcohol containing system is ethanol. And in terms of ether, CH3O, CH3 is the example, which is called as methoxymethane. And this is called as ethanol. Okay. The name of this compound is ethanol. And the name of this compound is methoxymethane. So why it is called as methoxymethane? So one is taken as alkoxy. The other one is taken as alkane. So alkoxyalkane. The one which is having a very less number of carbon atom containing alkyl group will be taken as alkoxy. Since both our groups are same here, I have took one as methoxy. Okay, methoxymethane. Now you can see the formula is same for both, but the functional group differs. Got it? Got it? Shall I move on with the next pair? So what is the next pair, students? It is aldehyde and ketone, right? So RCHO is aldehyde and RCOR is ketone. So and the example is same here. One is propanol and the other one is propanone. So this is called as propanol, and this is your propanone. Formula is same, functional group differs. One is aldehyde, the other one is ketone. Okay. Now coming to the third pair, that is cyanide and isocyanide. So CN is cyanide and NC is isocyanide, right? So methyl cyanide and methyl isocyanide. Okay. So these are the examples. You can see they are possessing same formula but different structures. Coming to the fourth pair is acid and ester. The functional group for acid is COH and for ester it is COOR. And the example is C3H6O2. One is propanoic acid and the other one is, what is the other one? It is methyl ethanoate. Okay. So since we are having 3 carbons here, it is called as propanoic acid. And this compound, it is called as methyl ethanoate. Okay. It is methyl ethanoate. Okay. RCOOR, right? And this R group is CH3. And this R group is also CH3 here in this system. Now the R group which is attached to oxygen, they has to be taken as alkyl. They has to be taken as alkyl. Alkyl alkanoate. Alkyl alkanoate. So this alkyl is methyl for this example. So it is called as methyl. And here one carbon and here one more carbon in CH3. So it is called as ethanoate. Methyl ethanoate. Clear? Clear, students? Shall I go with the next pair? Yes or no? Say something. Yes. Yes, the fifth pair is alkene and cycloalkane. Alkene and cycloalkane. The formula is CnH2n for both. And example for alkene, yeah, the same example which I have given you is to you on the screen also. One is propene. This compound is called as propene. And this is called as cyclopropane. This is cyclopropane. So both are having same formula, but one is unsaturated and the other one is saturated cyclic system. Got it? Clear for all? Any doubt in the functional isomerism? Shall we go on with the fourth isomerism? So what we have completed so far? We have completed chain, positional, functional. So the last isomerism under structural is metamerism. The fourth isomerism is metamerism. So what is metamerism? And it arises due to the different number of carbon atom on either side of the functional group or heteroatom in the molecule. So what is meant by hetero? What is meant by hetero? Hetero means different. Hetero means different. So between or adjacent to the heteroatom, we are going to have different number of carbon atoms. Got it? I'll show you an example so that it will be very clear for you. So C4H10 was taken as an example. So in the first compound, you can see, so this is the heteroatom. The atoms which are other than carbon, they are called as heteroatom. Okay, oxygen is the heteroatom here. And to the oxygen, 2 R groups are attached. Okay, so basically this is ether. ROR, no? So it is the ether functional group. And you can see in the first R group, we have only 1 carbon atom which is called as methyl. Only 1. And in case of R dash, how many carbon we are having? 3 carbon we are having. So this is methyl and this is propyl. Okay, here 1 carbon we are having and here 3 carbons we are having. But for the next compound, this is your ether group. On both the sides, both the R groups are having 2 carbons each. 2 carbons each. So both are called as ethyl. Okay. So you can see different number of carbon atom on either side of the functional group. Different number of carbon atom on either side of the functional group. Here 1 and 3 and there 2 and 2. So these compounds are represented, or it is called as metamers. Okay. Clear? So the name of this compound is methoxypropane, and this is ethoxyethane. Ethoxyethane. Okay. So metamerism exists not only in ethers, it also exists in some other functional groups. Okay. But there is some criteria. So if you have a functional group, then on both the sides you should have alkyl group. Or simply I can say that you should have a symmetrical system. Symmetrical functional group should be there. So in all the symmetrical functional group containing compounds, metamerism exists. Okay. I'll show you some examples. Ether is the first group, and examples to you on the screen. So for a metamer, at least 4 carbons should be there in the compound. If you're having 3 carbon containing ether, then you cannot show the metamerism. Like for example, if I'm having CH3O C2H5, here I'm having only 3 carbons in total, right? So will I be able to draw the other isomer for this particular compound? Will I be able to draw? If I'm able to draw, what can I do? I can write the C2H5O and CH3, right? So again, the compound is same. Both the compounds are same only. Both the compounds are same only. This is called as methoxyethane, and this compound is also called as methoxyethane. Both the compounds are same. So with the 2 carbon or with the 3 carbon, we will not be able to write the metamer. So at least we should require 4 carbons minimum to write the metamers. Got it? For ether. And for amine. So we have primary amine, secondary amine, tertiary amine system. So among these 3 amines, only secondary amine will show metamerism. Only secondary amine will show metamerism. Okay. So what is the formula for primary amine? RNH2 is primary amine, and RNHR is secondary amine, and RN is called as tertiary amine. So in primary and tertiary, you cannot see or you cannot observe the metamerism. So only in case of secondary amine, you can observe the metamerism, because that is the symmetrical system. That is the symmetrical. So that contains 2 alkyl groups attached to it. Whereas in case of primary and tertiary, you have 3 alkyl groups attached to it, right? So it is not observed in those 2 cases. And for amine also, minimum 4 carbon is required. Got it? Now coming to the third functional group, it is called as thioether. So usually we write thio for representing the sulfur, right? So instead of oxygen, if I'm putting sulfur, then it is called as thioether. For this also 4 carbon is required. And the last one is ketone. Ketone is an example for symmetrical functional system, right? So RCOR, it is symmetrical. And here, a ketone requires minimum 5 carbon. It requires minimum 5 carbon. Why? So already 1 is there in the CO. In the carbonyl carbon, we are having 1 carbon. So alkyl groups, they should contain at least 4. Then only 4 plus 5 will become 4 plus 1 become 5. Okay. So for ketone, minimum 5 carbon is needed to draw the metamer. And for the other system, minimum 4 carbon is required. Got it? So these are the some of the examples where metamerism would exist. Got it? So students, any doubt in metamerism? So any doubt in the metamerism? Shall we move on with the next isomerism? Yeah. Besides the functional group, number of carbon atoms must be greater than or equal to 4. That is what I have told you. So you can see. So a ketone with the 4 carbon, they do not show any metamer. So a ketone should have at least 5 carbon. A ketone should have at least 5 carbon. Then only you can observe the metamer. Got it? This is what I was explaining to you. And coming to the second isomerism, which is called the stereoisomerism. So structural we have completed. So under structural, what we have discussed? Chain, position, functional, and metamer. So in chain isomerism, same molecular formula but different carbon skeleton. In positional isomerism, same molecular formula, different position of the functional group. And in case of functional isomerism, same molecular formula, functional group itself will be differing. And in case of metamerism, same molecular formula, but different number of carbon atoms attached with the functional group. Okay. So these are the 4 structural isomerism. Now the second division is stereoisomerism. So what is meant by stereoisomerism? The compounds that have the same constitution and sequence of covalent bonds but differ in relative position of their atoms or groups in space. So where do they differ? They differ in the relative position of their atoms or groups. So simply, how can I define this stereoisomerism? Means different spatial arrangement of atoms. Compounds having same molecular formula but different spatial arrangement of atoms or groups is called as stereoisomers. Got it? Compounds having same molecular formula but different spatial arrangement of atoms. So in a given space, the arrangement of atoms would be different. That's all. That is stereoisomerism. Okay. So now under stereoisomerism, I have told you there are 2 types. One is geometrical isomerism and the other one is optical isomerism. Okay. So coming to the geometrical isomerism, so it arises due to the restricted rotation about the carbon-carbon double bond due to the sidewise overlap of pure p orbitals. So we all know that the carbon-carbon, that pi bond is formed by the sideways overlap of the 2 p orbitals, right? So what is the shape of p orbital? What is the name of the shape of p orbital? You might have studied the shapes in chemical bonding lessons as well as in structure of atom lesson, right? The shapes of the orbitals. S orbitals are spherical in shape. And what is the name of the p orbital? Yeah, it is dumbbell shape. It is very good. It is dumbbell shape, right? So you can see the p orbitals here. Yes, good. It is dumbbell shape. So here, ethene is taken as an example. That is C double bond C and HH and hydrogens are attached here. So here one is sigma bond and the other one is pi bond. Sigma bond is formed by the head-on overlap of the hybridized orbital, whereas the pi bond is formed by the sideways overlap of the pure unhybridized p orbitals. Unhybridized p orbitals. They are overlapping in a sideways manner to give the pi bond. So now, when you rotate this bond, when you try to rotate this bond, so try to keep one carbon fixed and try to rotate the other carbon. If you rotate that, what happens? The p orbital, the p orbital, it will try to go to the perpendicular direction. So what happens there? So the interaction between both the orbitals, it is breaking down. That should not be the case. No, that is not possible. So because of that, the restriction is rotated. The restriction is, the rotation is restricted. Sorry, the rotation is restricted. Got it? Carbon-carbon double bond rotation is restricted. So because of this particular restriction, there arises an isomerism called geometrical isomerism. Okay. So you see, the first condition for geometrical isomerism is a compound should have at least carbon-carbon double bond or carbon-nitrogen double bond or nitrogen-nitrogen double bond, or it must be a cyclic compound. This is the first condition for geometrical isomerism to exist in a system. And both the atoms or groups joined with doubly bonded carbon must be different. They must be different. Okay. So in the last case, we have seen that all the 4 hydrogens which are attached to the double bonded carbon, they were same. That should not be the case. They must be different. They must be different. You can see here, they are different. So here we have, for this particular carbon, we have A and B different system, and here also we have 2 different systems. Okay, at least 2 groups should be different among the 4, and for the particular single carbon, and those 2 should be different. Got it? This is the case, and A should not be equal to B. A should not be equal to B. That is, AB should be attached with the first carbon, and AB should be attached with the second carbon. Okay. Now, for this particular system, if you can find the similar groups on the same side of the double bond, then that particular isomer is called a cis isomer. So here you can see both are A. So they are similar groups, or the same groups we can say. So the similar groups, they are present on the, or they are located on the same side of the double bond. They are on the same side of the double bond. Both are towards upward direction, right? They are on the same side. So if you can see the similar groups on the same side of the double bond, it is called as cis. If you can see the similar groups on the opposite side of the double bond, then it is called as trans. Then it is called as trans. So you see the similar groups are on the opposite side. A is on the opposite side. So it is called as trans. Okay, very easy. This is very easy. Okay, no need to worry about it. So this is about the condition for isomerism, geometrical isomerism. One is cis, the other one is trans. Geometrical isomerism is otherwise called as cis-trans isomerism. It is otherwise called as cis-trans isomerism. Very easy. Okay. So understood, right? So students, any doubt any of you have so far in the geometrical isomerism? Let's discuss this with an example. If you have any doubt in between, you feel free to ask. Okay, I'll explain you again. So the example that I took here is butene. Butene. How many carbons will be there in butene? Can anyone tell me the number of carbons present in butene? What is the total number of carbon atoms in butene? Can I have the answer soon? Yes, very good. Samsung Lab 2. Yeah. Yes. Good. May I know if there is only one person behind Samsung Lab 2, or there are more number of students watching behind that same ID from Samsung Lab 2? Okay, you just work on it and you go with the class. So in butene, we have 4 carbons with 1 carbon-carbon double bond between carbon number 2 and carbon number 3, right? So this is butene. 1, 2, 3, and 4. Between carbon 2 and 3, we have double bond. That's why it is called as butene. So between, this is carbon number 1, 2, 3, and 4. So you can see same ID but separately. Okay, so there is only one person behind that ID, right? Okay, no problem. Okay, no problem, dear, no problem. Just want to know your name, that's it. Fine. To the second carbon, you can see there is only 1 hydrogen and 1 methyl group, and those 2 are these 2. And for the third carbon also, 1 hydrogen and 1 methyl group is there. So you can see the similar groups. Methyl is one group. I can take methyl as A and hydrogen as B. And you can see the similar groups are on the same side of the double bond. So what is the name of this isomer? It is cis isomer. It is cis but-2-ene. Okay. So this one is your trans but-2-ene. The similar groups are on the opposite side of the double bond. So it is called as trans but-2-ene. Okay. You should not get confused with this. You should not write like this. For example, if I am having like this, will this compound exhibit geometrical isomerism? You guys tell me. Tell me whether this compound will exhibit geometrical isomerism or not. Yes, the answer is no. Very good, Anjanasri. It is no. Answer is no. Why it is no? Because similar groups are on the, you can see they are attached with the same carbon. This compound will not exhibit geometrical isomerism. So both the double bonded carbon should have similar groups attached with it on the same side or opposite side. Got it? So these are some of the confusions you will get in your exam. So you should be very clear with this, which is easy, but you have to be very careful also. Okay. So this is an example, very common example for geometrical isomerism. I hope geometrical isomerism is clear to all of you. Okay. So let's try to solve this question. Draw the cis and trans isomer of the following. So first you tell me whether the compound A will exhibit cis-trans isomerism, that is geometrical isomerism, or not. What is your answer? Will the compound exhibit? Yes, answer is yes. Okay. So what could be the structure? What could be the structure? So it is, this is the carbon. These two are the double bonded carbon. And to that carbon, one hydrogen is there and one chlorine is there with the first carbon. Yeah, and with the second carbon also, one hydrogen and one chlorine is there, right? So the similar groups are on the same side. So this is cis and the other one is trans. Fine. What about for the second compound? Will the second compound exhibit cis-trans? Will the second compound exhibit cis-trans? Yes or no? Yes. Very good. Answer is yes. So hydrogen is one group and COOH is the other group. If they are on the same side, it is cis, and if they are on the opposite side, it is trans. That's all. Very simple, right? So I'll go with the next classification, which is the last classification of the whole isomerism. And this will come under your stereoisomerism. The first stereoisomerism was cis-trans, that is geometrical, and the second stereoisomerism is optical isomerism. So before moving on to optical isomerism, you should know what is optical activity first of all. Okay, then only we can able to find out whether the given compound is optically active or not, or whether it will exhibit optical isomerism or not. So to make you understand with this concept, so I'm starting with taking an ordinary light. So an ordinary light will give light in all the directions, right? An ordinary light will give light in all the directions. Okay, in all the directions, you can find the light from an ordinary system, ordinary light system. And if I am passing this ordinary light through a nickel prism or through a polarizer, so the ordinary light which has given light in all directions, now it is going to give light only in one direction. Okay. So if I am passing the ordinary light through a polarizer or a nickel prism, I am getting a plain polarized light. Plain polarized light will give light only in one direction. Okay. So now if this plain polarized light, you can see it is giving light only in one direction. You can see the waves passing through that particular direction. Okay. Now, if I am passing this plain polarized light in a solution, okay, it will give two different systems. if I am taking an optically, let me take this solution as optically active solution. So I am taking optically active solution. Okay. If the compound is optically active, then this compound will rotate this plane polarized light in two different directions. If a compound is optically active, that compound will rotate the plane polarized light in two different directions. Okay. So this is the plane polarized light, which has given light only in one direction. Now, after passing to this, yeah, that's what. I'll tell you what is optically active. Okay. So if I am passing this in an optically active solution, now that compound will rotate the light in two different directions. One is through clockwise and the other one is through anti-clockwise. So what is the first one, clockwise or anti-clockwise? It is going towards right side, right? So it is clockwise. Clockwise is otherwise called as dextro-rotatory. Okay. The other one is rotating the light through anti-clockwise. So the other one is anti-clockwise, which is called as levo-rotatory. Dextro-rotatory is represented by a small d or plus, and levo-rotatory is represented by small l or minus. Okay, this plus and minus and the small d and the small l, they denote the optical rotation. Okay, they denote the optical rotation. That is, it is through clockwise or anti-clockwise. So that thing they are representing. Okay, now if it rotates through two different directions, then it is sure that the compound, the solution is having two different compounds, and that's why two different rotation is observed. If two different rotations are observed, then obviously it is clear that the compounds are isomers. We are having isomers and they are optically isomers, optical active compounds, which are nothing but optical isomers. Got it now? If you're having an optically inactive compound in a beaker or conical flask, we would observe only one direction rotation. We will not observe two different rotation. Got it? Only optically active compounds will show two different types of rotation. So they are called as isomers of each other. Got it? I'll explain you more clearly. Yeah, you can see the optically inactive compound, they will have only one type of rotation. For a compound to be optically active, the condition number one is the compound must have at least one asymmetric carbon. What is asymmetric carbon? It is chiral carbon. It is chiral carbon. So in our exams, we are not going to do experiments and see whether we can able to observe two different rotations or not in the examination, right? So what we have to do, we have to follow some rules. Just by seeing the question on the paper, we are going to find out whether the compound is optically active or not. Okay. So the condition number one is it should possess at least one chiral carbon. What is a chiral carbon? What is a chiral carbon? A carbon which is attached with four different atoms or groups. A carbon which is attached with four different atoms or groups that are called as chiral carbons. Okay. So now you can see A, B, C, D. Four different atoms or groups are there. So means that carbon is a chiral carbon. Okay. So all the groups should not be equal. If you're having a system like this, then that compound is optically active. And the example is here to you. So this carbon is optically active because it has one hydrogen, one methyl group, one OH group, and one COOH group attached to it. Okay. So all the four groups are different. So it is a lactic acid and this is a chiral system which is optically active. And you can see one more compound, tartaric acid to you. So how many chiral centers are here in this compound? Can anyone tell me the number of chiral carbons attached? are present here in tartaric acid? 3? No. There are only 2, na? There are only 2. So these 2 are the chiral carbons. These 2 are the chiral carbons. So these 2 cannot be the chiral carbon because they have C double bond OOH, right? So only 2 chiral carbon we are having and the compound is optically active. So condition number 1 is chirality. Condition number 2 is the compound must have non-superimposable mirror image relationship. Non-superimposable mirror image relationship. So you see, the compound or the isomer which rotates the plane polarized light is rotating towards clockwise, that is right hand side, which are called as D isomer. The other one is through left hand side, which is called as L isomer. Got it? So they should have non-superimposable. So what is meant by non-super? So suppose if I am taking my hand, this hand. If I am taking the mirror image of this hand, I will get this hand, right? Now what I am going to do, I am going to take this hand and try to place it over this hand. So now I can see the system is non-superimposable. Why? Because I'm having, it is differentiated by these 2 fingers, right? This particular hand is not superimposed over the other hand. Means they are non-superimposable. So a compound should be non-superimposable. If it is non-superimposable or if it is having non-superimposable mirror image relationship, then it is optically active. It is optically active. Got it? So take one compound, the same compound. If I am taking Cl and Br, I'll take, I am going to take the mirror image of it. So what I'll get? So this side I'll get COOH and here H and here Cl and this side Br I'll get. No. Now what you do, you take this compound and try to place it over this compound. So above this Br, who is going to superimpose? COOH is going to place over the Br. So that should not be the case, right? Then it is clear that the compound is not superimposed over each other. So we can clearly see that there is a big bromine at the bottom part, or it is below COH. So it is not superimposed, means the system is optically active. Okay. So I have shown you the 2 compounds on the screen. So we have only few more minutes. So can you try to find out the number of chiral carbons present in both the cases? In first compound, how many chiral centers we are having? Try to find it quickly. The number of chiral carbons present in the first compound. How many chiral centers are there in the first compound? So this is your chiral carbon and this is the another chiral center. Any other is there? So there are only 2 chiral centers in the first compound. And in case of second compound, how many chiral centers are there? So this is one of your chiral center and this is your other chiral center. So you can check with the number of groups. Yes. Yes, Sanjana Sri. It is 2. Answer is 2. Only 2 centers are there. So you can check it with the groups that are present around it. If you're having 4 groups around each carbon, then it is called as a chiral center or chiral carbon. Okay. So this is about all the 2 compounds here on the screen are optically active. Now the next topic is reagents. This we will discuss in the next class. Reagents in organic chemistry will go with the next class. So any doubts, students, from the isomerism? So how many types we have seen? So it was classified into 2. One is structural and the other one is stereo. So under structural, we had chain isomerism and positional isomerism. Third is functional isomerism. Fourth one is metamerism. And stereo is classified into 2. One is geometrical and the other one is optical. Clear? So this is what we have discussed, and in next class we will deal with the reagents in organic chemistry. Okay. So thank you so much for all of you for listening the class. If you're having any doubt, just take it to the next class. I'll clear it. Okay. Thank you. Thank you so much. Yeah, sure. I'll ask about your